Continuing with the second half of 2.1, where we're learning about vectors in the plane, we want to be able to represent vectors in their component form using trigonometry. So as we've said before, vectors have two distinct characteristics. They have magnitude and they have direction. Now sometimes those are the only two things you're given. So rather than being given an image, like a vector as a line segment, or rather than being given the components of your vector, you might be given these two key pieces of information, magnitude and direction. And in this case, the direction is given as an angle. So if we're given vectors information this way, we might need to reconstruct the vector so that we can put it into the component form, because component form is how we do most of our manipulations on our vectors. So we know that we have a magnitude of 4 and that we have a direction that is a negative 45-degree angle with the x-axis. So I'm going to draw that. A negative 45-degree angle would look like this, 45 degrees. And if we know that the magnitude of our vector is 4, then we could start to draw this visually using a directed line segment as a vector with an arrow pointing parallel to that negative 45-degree angle. And we could say that that vector is 4 units long. So from the initial point to the terminal point, this vector is 4 units long. Now that we know those two things, the magnitude and the direction, we can really reconstruct this image to look like a right triangle and use trigonometry. Starting from my terminal point and making a perpendicular with the x-axis, that's key. Make sure that you're using the x-axis. Do not use the y-axis to make your perpendicular. It needs to be the x-axis. We can turn this into a right triangle using the x-axis, our vector, the arrow, and this perpendicular line segment we just created. I'm going to copy that over. We're going to fill in the bits of information that we have, and then we're going to use Trig to find the missing components. So if this is our right triangle, we know that the hypotenuse, that's the side that is made up by the vector, that's 4 units long. We also know that the angle in this top left corner is 45 degrees. Now in our coordinate plane picture, we're calling it negative 45 degrees, but in this triangle picture, we don't need to include the negative 45. For simplicity, I'm going to leave it out. What we need is the x component, which is how far along is the distance in the x direction. So we're looking for that x component. We also need the y component, how far along vertically in the y direction. So those are the two values we need to find, x and y. Once we have those, then we could use them to mark the terminal point of the vector that we're looking for. And we can call this a position vector. Our initial point is at the origin. For any position vector, the coordinates of the terminal point turn into the actual components of our vector. So we just need to find the coordinates of that terminal point and then copy them into our new vector notation. I said we're going to use trig, and this is where it's going to come in. Remember that we have 3 main trig functions. That's sine, cosine, and tangent. Each one of these trig functions takes in an angle, and it converts it into a ratio of 2 lengths. Some of us use SOHCAHTOA to help us remember what the ratios are for each of these trig functions. I like to use a story that says, some old hippies came a-hoppin' through our apartment. So for the sine function, I know that it is opposite over hypotenuse. For the cosine function, I know it is adjacent over hypotenuse. And for tangent, I know it's opposite over adjacent. Looking at the three trig functions that we have, and also looking at the information we have within our triangle, we can see that the sine function will help us find the missing side y. And that's because sine uses the opposite, so if this is our angle, the opposite side is y, and it uses the hypotenuse, which we know is 4. So we'll use the sine trig function with the given angle and the given hypotenuse to solve for the missing side y. We'll set that up as sine of 45, whoops, that's not 45, sine of 40, what the? Let's try that again. Sine of 45 degrees is equal to the opposite side, that's the side y that we don't know the value for, divided by the hypotenuse, which is 4. We can solve this for y by multiplying by 4 on both sides. So we get 4 times sine of 45 degrees is equal to the missing side y. Similarly, we can solve for the missing side x. X is adjacent to the angle that we're given, and since we know the hypotenuse is 4, cosine of 45 is equal to our adjacent side x divided by our hypotenuse 4. Again, we'll multiply by 4 on both sides so that we have 4 times cosine 45 is equal to x. Now you might notice something going on here. The y component is the magnitude times sine of the direction angle. The x component is the magnitude times cosine of the direction angle. Now there's one tiny piece that we have not addressed, and that's the fact that the original angle is negative 45 degrees. And I've only plugged in positive 45 because of the way that I drew this picture. But if you think about where this terminal point should appear in the coordinate plane, it's pretty clear to see that y needs to be a negative value. So what we can do is remember that we have corresponding angles. So positive 45 in quadrant 4, negative 45 degrees, which puts you in quadrant 4, has the same sine output as positive 45 in quadrant 1 with a negative multiplied outside. If that seemed a little bit hand-wavy to you, come visit me in office hours and I can try to brush you up on some trig, or do a quick YouTube search for a trig refresher with corresponding angles. So we can type these into our calculator, or we can remember that sine of 45 is root 2 over 2, so our y value turns into negative 4 times root 2 over 2, and our x component turns into positive 4 times root 2 over 2. So the vector that we're looking for, instead of having x and y in a general sense, we can plug in the actual x value, which would be 2 root 2. And we can plug in the actual y value, which would be negative 2 root 2. So if we are given the magnitude and a direction angle for a vector, we can use trigonometry to convert back into component form, which will be useful for manipulating that vector. Let's try that same idea, but for a second problem. See if we can do it a little faster now that we've seen a little bit of how it goes. We want to find the component form of a vector with magnitude 10 that forms an angle of 120 degrees with the positive x-axis. I like to draw pictures to visualize, so I'm going to do that. 120 degrees with the positive x-axis is going to put us about right here. And a magnitude 10, I'll draw my vector so that it looks like it's got magnitude 10. Just so we know which quadrant we are in. In the last example, where we took the magnitude and direction angle and used them to find the component forms, we found a bit of a pattern, which was that the x component looked like the magnitude times cosine, sorry my cat's going crazy, times cosine of the direction angle. and then y was equal to the magnitude times sine of our direction angle. So once we know that those two things will get us the x and y components, these problems go much faster. So the x component would look like 10 times cosine 120. The y component will look like 10 sine 120. Type that into your calculator. Make sure that you're in degrees. Remember cosine of 120, sine of 120. If you're in radians, it's going to give you a much different answer. So for the vector, I'm going to call this vector W. My x component, 10 cosine 120, looks like -5. And the y component, 10 times sine of 120 degrees, looks like 5√3. So it's not as long and drawn out as the first example because I was building up the foundation for these two little shortcuts. Now that we know them, we can use these without drawing the triangle. However, if you forget which cosine and sine goes with x and y, you can always draw your triangle and rebuild that shortcut yourself. Unit vectors are special because these types of vectors always have a length of exactly 1. So by definition, a unit vector will have a magnitude of 1. If we have a vector that is not a unit vector and we want to grow the vector to be 1 unit long, maybe it was short and we needed to make it longer, or we want to shrink the vector so that it's exactly 1 unit long, maybe it was like 3 units long, we want to shrink it down to be 1 unit, then we're going to use this formula. This formula says take the vector v and then divide it by the magnitude of the vector v. Once we've done that, we can call this a unit vector where we use this new notation, a little hat on top. So v hat, that hat is only for unit vectors. It's totally okay to call a unit vector with a regular arrow on top. It's not okay to call a 3-unit long vector a unit vector using a hat. So we only use the hat if we know for a fact we're talking about a unit vector. Any vector which has a magnitude and a direction, they all do, we can rewrite them now using this unit vector as the direction. And from here forward, when, oops, I didn't mean to cross out direction. And to say from here forward, when you see direction, I want you to think unit vector. Similar to how we use a unit ratio or a unit rate of change to describe common things like price per unit or miles per hour, 1 hour being a unit, we want to use our direction vectors, unit vectors, to describe the way that a vector is changing its direction. So we'll use the unit vector as the direction, and then we can multiply that by magnitude. And that's what we see in this formula here. Any vector v can be written as a product of two things. We have the magnitude of v times the direction of v. So the last factor here is the direction of v. Let's try an example. If we want to find a unit vector for the vector v, where the components are 1 for the x direction, 2 for the y direction, what we need to do is find the magnitude of v. Remember that the magnitude comes from squaring each of the components, adding them together, and then square rooting them. So the magnitude of this vector would look like √5. Once we have the magnitude of v, we can create a unit vector that is essentially parallel to the original vector v. So I'm going to create my unit vector. I'm going to call it u hat. U because it's unit vector, hat also because it's unit vector. So I'm trying to be crazy obvious that I'm talking about a unit vector here. This unit vector is going to be in the same direction as v. So I'm going to use v divided by the magnitude of v. That will look like the components of v. So 1, comma 2 in my numerator, divided by the magnitude of v, which we said was root 5. And there's many ways to write the answer here. I can leave it like this, with the pointy brackets in the numerator and the magnitude root 5 in the denominator. Or I can write it as 1 over root 5 times the vector 1, comma 2 with pointy brackets. Or I can multiply that scalar, 1 over root 5, into my vector so that I have 1 over root 5, comma 2 over root 5, still using the pointy brackets because this is a vector. Now, at this point, I will always get a few students asking, do we need to rationalize this? The answer is probably not. The only time we really need to rationalize is if we're trying to solve equations that involve radicals in the denominator, because sometimes hidden solutions are overlooked because of the radicals. So in this case, either one of those answers are just fine. As for the homework program that we're using, make sure you read the directions carefully on what answer it's asking for. Although we don't have to rationalize, sometimes it's a skill that we need to practice, and so it will show up in some of our assignments. Okay, so we did the first one. We found a unit vector with the same direction as v, and that's any one of the 3 vectors that I have on the screen. These are all the same, just written in a slightly different form. The second one says find a vector w with the same direction as v, but we want w's magnitude to be equal to 7. Now remember that I said when you see the word direction, I want you to think of unit vector. We just created a unit vector that's in the direction of v. Now we're going to use the second concept, which says you can create a vector by multiplying the magnitude you want times the direction you want. So the vector w, we want it to have a magnitude of 7, and we want it to have the direction of u hat. We know what u hat is, so let's plug in the components. Any version of it you want, I'm going to use the 1 over root 5, 2 over root 5. And we're done. The vector w, this vector, definitely has a magnitude of 7 and a direction parallel to v. Again, you can write this in different forms. I don't want to get nitpicky here, but I do want to take a second to say there are multiple versions of the correct answer. Lastly, we're asked to find a vector with magnitude 5 in the opposite direction of v. That's very similar to what we just did with w, but this time we're not going to use u hat for our direction. We'll use negative u hat. So maybe we'll call this next vector s, vector s, and I want that to have a magnitude of 5, and I'm going to have a direction of negative u hat. And we can plug in the negative u hat to get our final answer of negative 5 over root 5, comma, negative 10 over root 5 in pointy brackets. You'll see a few problems like this in your homework. You'll also see these ideas mixed into word problems. So if you get stuck on how to create a vector with a specific magnitude and a direction parallel to another vector, revisit this idea.